Hey y'all, everyone, thank you guys so much for being here. I know it's a Saturday afternoon for some of us and Saturday morning for those in on the West Coast. But we're here today with Mudit Agrawal. Mudit actually works as a principal scientist lead in the mixed reality HoloLens team at Microsoft. He leads the efforts in iris recognition in biometrics and health diagnosis. Prior to this, he worked at HP Research Labs in the area of handwriting recognition. His expertise lies in machine learning, image processing, document analysis, and biometrics. Definitely whole realm of computer science topics that we've all heard about. And lastly, Mudit has a PhD from University of Maryland, College Park, holds 9 US patents, and has published more than a dozen international papers, and is an avid mentor for startups and individuals. So without further ado, we can get started into the moderated questions. Another note for those to feel free to publish your questions in the session Q&A chat, and a moderator will throw them in, and we'll get to them near the end of our fireside chat. So yeah, we can definitely get right into it. So first off, Mudit, we want to just talk about your journey into computer science in general. So what has been your journey to where you are today, and what drove you towards engineering as a whole?
Mm-hmm. Yeah, first of all, again, thanks for giving me the opportunity. It's a great platform. I hope we all learn from each other in this 1 hour. So again, thanks, many thanks. Yeah, so to your question, I guess I'll start with a famous man's words, right? That you cannot connect the dots looking forward, and only when you look backwards, you can connect the dots. So when I look backwards, I cannot really imagine any other path I could have chosen other than engineering. So that's basically because even though my dad probably wanted me to be a doctor, it was my obsession with batteries and electronic cars and creating things. Anything electronic was very clear that I want to be, an engineer. Well, I did turn to be a doctor, PhD one, but not the one he wanted, right? But yeah. But in my 5th or 6th grade, when I was introduced to computer science, that was a very different sensation. Now, I'm not really a love at first sight kind of a guy, so that thing kind of grew over me, over time. And that time when we then started doing programming, and it was all in BASIC, COBOL, and Fortran that time, but it was very, very intriguing. I think it was basically the limits of imagination. What we were doing, our experiments or what we learned in chemistry, it was limited by the chemical composition of the compounds, whatever you could create or experiment. In biology, again, the nature's laws and physics, mathematics everywhere, but it was basically programming where, it's really what you want to limit. You create your own laws, and you want to create a game under your own laws of physics, you create, here you go, you have one. So I think that was very fascinating to do that. Also, I feel it was, the curiosity. I'm very, very curious, been very curious. So that, and plus I love building things. So if you see it, engineering is the use of scientific principles to build things. So that basically combines a curiosity to know the scientific things and building. So that's kind of, I think the perfect fit for me. Now, that said, I was still very inclined to being an architect. And that was because of my passion in building things. I used to make miniature models of cars and houses and whatnot. So it was basically that decision whether you really want to be an architect or maybe a EE or a CS major, what do you want to choose. That was a hard one. But again, it was the CS building was basically the opportunity you have, as I said, limits of imagination. But that said, the real decision came through an opportunity at a college which had one of the best professors in computer science back in India at that time. And that was probably my a first kind of a suggestion, right? That the professor can change your life, for good or the bad. So you got to choose carefully, right? And many times we feel that our inclination for a subject, no matter how much you think it's your choice, is really a weighted sum of how good that professor or teacher was, your intrinsic ability in that area, and your surroundings, and so on. So I think it was really, so some boring courses in undergrad became very interesting in grad school when there were the right professors. So many times it was that, right? At the same time, I was also lucky, I would say, as a child, we had a kind of a joint family, and my grandpa's younger brother used to live next to us, and he was an amazing mathematician, right? So he taught me fundamentals of mathematics in a way which were applied in real life. So if you're learning about parallelograms as a kid, or rectangles and their properties, he would really take some practical examples and say some tribal area, and how they actually know this without really knowing it. So that was very intriguing. One thing I still remember was that when he read the chapter of matrices, which he never learned as a kid, and he's like, yeah, I understand all these numbers put together in a box, but I don't exactly know what their application was. And that's exactly where my interest fell. Like, yeah, I don't think it's really worth it to remember, right? But when I took the linear algebra and computer vision in my grad school, that connection was very clear. That's like a fundamental building blocks of how these things would work. So again, it's really about the right teachers, lucky enough to have those, and finding the right problems, which really excited me.
And to like follow up to that question, like obviously you might have touched on this like after your undergrad and into your PhD. But why did you choose image processing and machine learning as kind of your specialization?
Yeah, that's a long journey, and we can probably divide it into two parts. So I'm first of all a very visual person, and in image processing, what intrigued me was that how we could manipulate an analog real world in front of us, what we see through our eyes, to a digital world and play with it. And that was really fascinating, because I still remember I think that it was the first or second chapter in the digital image processing book. It was Gonzalez and Woods, where they talked about how our eyes are like a biological camera with its own limitations and blind spots, and how evolution has best enabled or not enabled us to use it. How they're capturing scenes of the outside world with the photons striking the retina, with its own rods and cones distribution, and again, all that with its own sensitivity towards light, the optic nerves carrying it to the brain, and then all that is basically a sensor optic system at the end of the day, and how a brain manipulates it. It's amazing, and we could actually replicate the whole exact system in computer science or computer engineering. So that, I think, was very intriguing. And again, that part itself of a brain is one of the major processing hubs, right? We spend a lot of energy in visual systems of visual cortex of the brain. So, and then at that time also, image processing was a very unsolved problem. It was just budding, and very simple problems to humans, like classifying dogs and cats, were very hard for image processing. And you were like, hey, there's very orthogonal challenges in computer science, right? Compared to like, you could probably not do a power sum or something, but a calculator could do it in seconds, and vice versa. You could do very easily classify objects in the visual world, whereas it was super hard to do it. So that was, I really thought was a wondrous thing to replicate in machines. Now, if you thought that was awe-inspiring, my next semester was a pattern recognition class. That was basically, these courses were, first of all, in my freshman and I think it was pretty much freshman year, I took as many courses to diversify my portfolio, to understand what all things I can actually play with. And then that pattern recognition class was basically then the next step. So once you have all that signal being carried through the optic nerves to the brain, how does your brain perform after sensing? How do we extract features, segment, group, classify, post-process? So I think that was very clear that image processing and then pattern recognition or machine learning, you could call it, it's a broader subject area, was my area. Now, I did have some liking towards graphics. Again, coming back from my inclination towards architecture side of building things. But again, the curiosity to decipher and decrypt the wonders of the nature through the eyes of a camera triumphed the building of an imaginary world through graphics. Still, it was a pretty hard decision, but it was that one. Yeah.
Thank you for that answer, Mudit. And it sounds to us that your experience in grad school really did shape your journey and help you develop the passion for what you do today. And we would love to know what advice do you have for those considering pursuing graduate school?
Yeah. So that's I would say, first of all, grad school. I would say a few things. First of all, higher studies, in my opinion, is always a good option. In your undergrad, 4 years of undergrad is awesome, but it's really the grad school, whether it's a master's or a PhD, that picks up a stream and starts carving it out, right? And that's where you start digging deep and understanding exactly what the problems in an area are. And really, it's up to you how deep you want to go there. But really, whether you want to do a master's or a PhD. But that's where I think the rubber meets the road, in my opinion. Now, also, I feel that you could argue that one could, there are a lot of opportunities, especially in industry, especially in CS, EE, where you could actually get a job right after your undergrad. And yes, it's not a bad choice for sure. You could do that. But I think from the way I see the world, I think it's always good to hone a specialization, because that takes you really far. It really makes you understand the bare metal, really understand where the edge of the challenges are, the technology is. And then you can come out and explore different avenues. It's always good to first go as deep in any subject of your choice. So that's one. Now, regarding advice, if you really want to get to the grad school, and if you still feel, probably I should put another 2 years, I would say always get good grades. It's important because your application needs that. Research professors of interest, their work. Spend a lot of time, late nights after my undergrad, researching, talking to professors. If you can visit them, always better. Go and visit them. Talk to their students, grad students. They would tell you how things are going, what the funding situation is if you are in need of funding for your grad school. Also, many times, some professors tend to have huge number of students, so they have less time for individual ones. So that is becomes also clear, because what kind of advice you're looking for from a professor. And at the end, lock yourself in a room and switch off your internet and ask yourself really what you want to do, and translate that into a statement of purpose. And that, I think, is a very big weapon when it comes to grad school. Because when they read it and they understand, of course, it has to be backed by your own ability of, as I said, your grades, and of course, recommendation letters. As in your final senior year of your undergrad, if you have inclination towards grad school, start talking to professors already in your university or college. And if you could publish or even write a white paper in an area of your choice, that really helps. That means you have that inclination towards research. But the final thing I would say is, once you get in a grad school, you're not married to your SOP. Don't treat it as a Bible or anything. You don't have to stick to it what you thought it originally was very important to you. Because now you have a great opportunity. You have much wider aspects perspectives which you would be seeing. So reevaluate, experiment and choose again.
Yeah, and after you do have this experience in grad school and you move on to the corporate world, what does technical research look like in a corporate setting? Especially when comparing to this kind of technical research that you do in graduate school. How is it different, and how do you go about that?
Yeah. So maybe I'll start with where the traditionally how they looked, and then later I'll come back to where they are kind of moving, especially in computer science. So traditionally, I think academic research is more discovery focused. So much research is basically done for the sake of learning as opposed to application. So tech research always has a purpose and is mainly tied to a business proposition. Now, it can be open-ended, but usually needs to translate to a real-world problem. Now, in many ways, you could say that the tech research is similar to the proposal of your PhD, where you have to justify that the problem really exists. Your solution is a great one, and it can actually solve the problem which you're going for. But then, in addition to these three, the in tech research would ask you, how would it make our lives better and bring revenue? Because at the end, it's a business. Now, the great example I tend to give is like, you could have a proposition to fix craters on moon. You could say, hey, your moon has so many craters, at night it shines, but yeah, I can still see those black spots. I don't like it. But here's the way, you could send a robot on the moon, and in 50 years, it'll start doing blah, 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 and it's going to fix it, and this is my solution. It's amazing. Sure, but who cares? I mean, at the end, what revenue does it bring to me? Unless you prove that, it would be hard. It can be great academic research because you'll have a lot of challenges on a low gravity, less atmosphere, sphere in the middle of vacuum, and how to fix it. But that's the part. Now, that said, there are some bads and the goods also, right? The first bad about tech research, industry research, is that rarely new research ideas are germinated in industry. Now, I'm saying this with a caveat, and I'm squinting, but still, it is usually true. Because a lot of heavy lifting is needed first to get the ball rolling, so as to say, right? Now, academia is a great place for that, and you could see examples, like even AR, VR. The first paper by Paul, I think, was University of Toronto, or in machine learning algorithms, whether they are SVMs or neural networks or HMMs, anything of that sort, all academia. So the way to imagine this is that if you have a feature space of all possible ideas, and you were to sprinkle research papers into this space, they will pretty much cover the whole space like salt and pepper. However, the tech research would choose areas of interest, which can, of course, solve a problem, and they will be much more dense. They'll be spotty, but more dense in those areas. But the good part is that the tech research, once it understands the problem, it really solves it. It goes to depths of getting the right data set, right kind of solutions to it. Now, I could say that an example is actually biometrics. So you would have seen papers in fingerprint recognition for many years. It's a very oldest probably biometric we have known. Then came face, and then came iris. However, all the papers were, if you have seen their implementations also, you have to keep the fingers very tight on the glass surface. You probably have to even rub it or move it around, and nobody cared about the user experience there. And it was not, I think, until when it was done on an iPhone, where you just tap it and you're logged in with pretty good security, 1 in a 50,000 false accept rate. It's a very different ball game. You are looking at a very small part of fingerprint, and finding still features which can give you the same amount of security as like rolling the whole thumb around it, right? So from a stat perspective, you have reduced your degrees of freedom substantially. You still want to encapsulate the same signal out of it, the signal to noise ratio for that matter, right? So that's an example again. Now the hybrid model, which I said, the latest what is happening is that these differences are now getting muddier, right? The boundary is not as distinct as it used to be. First reason being, you see now professors, especially in, again, computer science, they are in industry for a few years, they're back to colleges. Similarly, researchers and professors, they are like, moving back and forth. So there's a lot of cross-pollination is happening there. And then also in academia, just to give the right credit there are projects which are funded by, say, NSF and some other foundations, which really require them to have the code from the grad students, especially even undergrad. And there, fundamentally, you are solving a problem in the real world. An example was in my PhD, there was a project where we were supposed to do page segmentation. And OCR was kind of a solved problem, right? Like, of course, OCR, Latin script, very, very well written, and you could understand where the paragraphs are, where lines are, where word is, and even if you can decipher them if you want. But the challenge of the project which we got was that it was from the military, and they had all the Asian scripts, Arabic scripts and Indic scripts, handwritten and scanned by using poor scanners, and then binarized. And when we put that data set into the academic state-of-the-art algorithm, our accuracy went down from like 90% to 30%. That was a huge difference. And that's exactly what industry research looks like. When you look at the real world problems and you say, okay, let me implement this paper to my real data set, and like, oh wait, what just happened? So that does happen in both, even in academia, right? Where if the problem is real, data has been collected from the real world, you are really then solving a real world problem. And I think that's what I mean, that it's already happening, especially in neural networks, in DNN, because DNNs are democratizing the whole area. So you have these amazing data sets, which are huge, very challenging. But still, they are industry data sets, which probably are bigger at this stage, but still they are pretty much bigger than what it used to be in academia.
Thank you for such an insightful answer. I know that a lot of students, like me included, in like a lot of computer science, engineering students, especially like engineering-minded students, are like on the fence about grad school. So we really, really appreciate like your insight on that and like trying to clear that up. Another like question that we know that you're actually like a principal scientist lead. So like, how is that role different than like the normal like software engineering managerial role and like the engineering role that we usually like apply to and like are more often to seeing?
Yeah. So I guess the two parts to it, the scientist and the lead part, versus like a software engineer. Let me first talk about a scientist and a software engineer. Fundamentally, I would say it's a title based on some of the things you have done in the past. So if you have a PhD and you have spent some years, really looking into a problem and digging deep, or more on the math side of it, then usually it's a scientist role. Software engineer is a typical software engineer, where basically you have engineering experience in computer science, and you're basically solving the problem. But the leader part of it can actually be applied to anything. At the end, every software developer engineer is a leader in the area. They drive the requirements, the goals, and they provide solutions. So could be a scientist in their own area. But when as a scientist lead, basically what you're saying is that the problem is very researchy in nature, and you have to have a good grasp of what exactly the problem statement is, how we need to start carving out the right solutions, and hence you need to build the right team, have right experts into every field of it. Right, so that's where you would need kind of a scientist lead, which would basically be working with other scientists and more engineers. But then also engineers would be what I tend to call them research software developers. They know an area familiar to what you're solving. So, for example, in our case, they would be all efficient in machine learning, or they are aware of machine learning, either machine learning algorithms, or tools for machine learning, or metrics for machine learning. And then you are basically, with the kind of a sharper knife, you're trying to solve a problem. Yeah.
Thank you so much for that answer, Mudit. And now we kind of wanted to move on from talking more about like your journey, grad school, and like advice for students, and move a little bit more into a discussion about AI. And the first question that we had for you about AI is that there's a lot of hype around AI. And in your opinion, is it the real deal? And what changed in the recent past that made it so promising?
Yeah, that's my favorite question. So, in one of my recent podcasts called Market Meditations, I basically argued what intelligence is and what makes us intelligent, or perhaps not. And the way we define intelligence for goal-oriented tasks today, which are primarily focused on the prefrontal cortex of the brain, focused on compute. Now that part, if that is what you're talking about intelligence, right? So before AI, I'm trying to basically define intelligence itself, right? And then I can say, yeah, whether AI is true or not. So if your part of intelligence is that, that focus on compute, then that part I feel can easily be replicated in machines. In fact, it's already superseding many aspects of human intelligence. So it is a very real deal from that aspect. Now, to your second point, what really changed? Why is there a hype now? It's just because there's social media, and that's why people now just know every damn thing that pops up, and they talk about it. Yeah, that's also a reason. That's why Bitcoin is up. I don't know, right? But but it could be. But I think there is also fundamental difference, right? For example, when we talk about deep neural networks, right? That evolved over time, and that needs us to go back a little bit in time. So maybe 20-ish years ago, when people thought about AI, they thought about in a way, a very conscious way of decision making. So, and as an example, if you have to classify a character A versus B, the way we would think is, oh, how does my brain differentiate them? And you would come back with a very conscious way of understanding it. Oh, the A has these two lines which are at an angle, which could be between, I don't know, 20 degrees to maybe 60 degrees, and B has two curves on the side. It has to have a vertical line. So you are kind of going back to your conscious brain and arguing what features should I build to understand it. So that was kind of a first stage of kind of machine learning, where the features being crafted are very, very conscious. Then slowly it became a bit towards unconscious, subconscious, I should say, where feature extractors like scale invariant feature transform, or SIFT, if you have heard of, or difference of Gaussian, or histogram of Gaussians, LBP, PCA, so many features came up where they said, oh, wait a minute, you don't have to really exactly tell what features you use. You go at a pixel level, do some stats of how the pixels are distributed, right? Create some histograms and start classifying them, right? And those features, and of course at different scales and so on, or maybe start detecting just random edges in the scene, and then do some stats on them, put them in some bags of features, and start classifying. And that was interesting because that were definitely superior feature extraction modules. So it was kind of contradictory to the way we thought we imagine or see things. But then when DNN came in the scene, they were like, okay, step aside. I don't think you guys have to even think about how to craft features, right? What is happening there is that you have literally the input coming in as an input of the scene, of speech, it could be vision and images, and all the features are being crafted within the layers, right? And your output comes out on the other end. So you don't really have this visual way of feature crafting. In fact, interpretability of DNNs is a very hard topic. People try to understand what the heck is it really doing, and then you go and decipher it and say, oh yeah, maybe it is finding features which our brain does, and so on. So you basically are inverting the problem from a very conscious way of understanding, from a very subconscious, minute ways of finding those features. And that was step number one that made the big deal. You have this immense amount of compute which you're throwing at different scales of the problem. Now, to give a concrete example, think of scene in front of you. Likely it would be a monitor or some keys. And how do you classify that as a PC or a laptop, right? And you could say, oh, my conscious way of saying this is a rectangle, and then there's another rectangle or a parallelogram below it, and it has to be this angle. No, that's old way of thinking. Okay, the middle way of thinking is, oh, there are these edges, and I want to classify at some angles to it. Even not that. You basically take the whole image, and run some what we call convolutions, which are kind of finding some very pixel-like features at the first stage, right? It could be edges, it could be textures, it could be color gradients, whatever that is. And then you are in like a pyramid scheme, mapping them at different scales, again involving more and more convolutions, right, in a CNN, which I'm describing. And that way you are basically just building your features, just like our brain does, right? You have data coming in through our eyes, as I said, going back to your brain, and your neurons are activating different layers after layers, and there are billions and billions of neurons. And once that comes in, you have a much better understanding of the scene or an output. Now, that wasn't possible. Why wasn't that possible 20 years ago? Yeah, because there were no GPUs to do that much compute. Yeah. So that's the second reason why these things are improving. GPUs are a big deal. And third is data storage. You have now big amounts of data being stored in the cloud, being used across different systems. But at the end, I feel nothing works unless something becomes a platform. And what becomes a platform is when things are made so easy so that it can be deciphered by a common person. And that's where the role of great platforms, and I'm calling them platforms, but like TensorFlow or PyTorch or whatever you call it, they are around the world where anyone can actually pretty much pick it up, run some sample code and understand what's really happening here. So I think all these three things: the evolution of DNN, the big data, the GPUs, and at the end, democratizing all of this in terms of tools being available to every person in the world, is what basically pushing this. Now, we knew this is going to happen in 30 years, but we didn't have all that to get going.
Yeah, thank you so much for that super in-depth answer. And yeah, I agree with you. AI is in fact the real deal. But to follow up on that, we do have a lot of students here today, and just like me, a lot of us are thinking of like, when should we start investing in artificial intelligence as a career path, and more so as a college students, what classes or topics would you recommend us to get started in the AI space?
Short answer: as early as possible.
Yeah.
I say diligence eats intelligence for breakfast. So be diligent. Start as early. Now, there are a lot of avenues in today's world which didn't exist. There are amazing courses on Coursera, Khan Academy, all other online courses. You are directly hearing from the horse's mouth. So Andrew Ng or Jeffrey Hilton. Amazing courses which you could actually just do. And they are actually, especially Andrew's courses, I feel are very. He teaches very well. He starts from a place where you are and then takes you up from there. But at the same time, what we also see nowadays is a problem that people understand DNNs but are not aware of exactly the pattern recognition problem, the linear algebra problem. So if you're really serious about AI, I would suggest that start from a bit basics. So take a linear algebra course. Take a pattern recognition course. Learn about traditional classification methods like SVM, support vector machines, hidden Markov models, and so on. And these are pretty much still relevant and to solve a lot of our problems. Many times people just apply DNNs to I don't know, like 50,000 samples and a DNN, meaning with the millions of weights, it's really an overfitted problem, right? You're not really solving the right thing. So having the right classifiers, understanding what it needs before you jump to DNN, and DNN is like a big brother, right? It probably will solve the problem for you, but it'll probably memorize everything. There was an interesting paper where they kind of took a data set and they changed the labels of it. So it was an orange, but they labeled it as a truck. And there was a truck, they labeled it as an apple pie or something, whatever, right? And then they fed it to a DNN and said, okay, can you learn it? And DNN said, yeah, I learned it. Everything was garbage, right? But it learned it. So it can really memorize. That's a problem if you don't really pay attention to overfitting. Again, we can explain what overfitting is, but basically the idea is that you have to have a classifier which is meant for that data set. So hence the basic understanding of these courses in pattern recognition, traditional machine learning approaches, as I said, are important before we talk about DNNs. And then I would also say that actually take today these there are a lot of things like Raspberry Pi. Pick it up, make a problem, solve it. There are a lot of sample code in the world. There are some simple ideas. Take a Raspberry Pi, attach a camera, put it in front of your doorstep. You have, I don't know, 20 people who visit your house. Whenever they come in, it just looks at their faces and calls out their name. It's a very simple project. You can do it probably in a week or so with the code exists in the world, and you'll understand pretty much all the nuts and bolts of this whole system, right? Things like that, really getting your hands dirty there.
Yeah, some of the topics that you actually hit on are most of the topics that, like, here at UT, we have classes in data mining, AI, and neural nets, and those are the first intro topics that you were talking about that we kind of hit on. We've talked enough about AI, and now we wanted to switch into like AR and VR, which is something that you work hands-on with at Microsoft. So first off, for everyone watching, what is AR, VR first, in your eyes, and why is it important to you and to the world?
Yeah, I think I was listening to Charlie's talk an hour back or something in your forum, and I think he said we can talk about AR, VR for 45 minutes, and I very much agree. I can talk about it 45 days, but agreed. So I guess, in short, the experiences that occlude your view to present a digital experience, that is virtual reality. Now, for all I care, you are experiencing virtual reality when you are submerged in your video game on your PC, and when your friend sneaks in your room or your mom calls and you don't listen, you are having a VR experience right on your PC. You're occluded from the world of the real world, and you're all focused on the monitor. But the experiences that overlay graphics on the video streams of the physical world, or the physical world itself, they are augmented reality. And I feel AR has way more potential than just VR. VR is great in very particular scenarios, but it's VR that it's AR which basically takes the wider view here. But also, I would say that things are not really that binary. That's why I prefer the term mixed reality, which is between the physical world and the digital world. That whole gamut is mixed reality. The more you move towards the physical world of things and you're augmenting things on it, that's AR. More you move away from the physical world and more towards the digital world, that's basically the VR. But however, at the end, I want to leave with this kind of an impression here, right? For mixed reality, imagine a Venn diagram with 3 circles. There's a human, and then there's a computer, and then there's an environment. Okay, and in the center of this intersection, so human, computer, and environment, in the intersection of all these 3 is mixed reality. But before we get there, let's first understand what it means, right? So human and environment, when they interact, it's conventional reality. Newton sitting under a tree, the apple falls, it's all conventional reality, right? But then the human interacts with the computer. That's HCI. When you move your mouse, keyboard interacts with the computer, all that. And when the computer moves in the environment, that's perception. right? Again, a self-driving car in the world, that's all perception. Perception captures things, people's positions in the world, surfaces, boundaries, ambient lighting, object recognition, and so on. But it's all the interaction between all these three things what makes MR really, really beautiful. Think about like when a computer perceives something in the environment and needs that to be overlaid in a way that can be perceived by human, right? For example, in surgery, the cameras on a device are understanding the objects in this humans in the scene, and uh, they understand exactly where the precision should be made. But now they need to that's perception, right? The computer's understanding the scene and where the incision should be made. But now they want to overlay that information as a surgeon's head is navigating in the space, right? Such that the incision point does not move an inch from the desired position, right? Helping the surgeon to in their task. So that's like one way of doing it. The other direction you could say is when we interact with the environment through our eyes, through our hands, through speech, and things pop up as properties in the environment. Now that's the other way of looking at it. And the third way is when the computer understands the human and readies them for their task. You're putting on the device, and it looks at your hair and your forehead and your eyes coming in through cameras looking into your eyes, and logs you in without even you entering a password, and loads up your eye tracking profile, adjusts the holograms based on your pupillary distance, gives you experience tailored for your eyes. In all these three ways, as I moved between these three circles in the Venn diagram, you're experiencing mixed reality.
That was a really in-depth answer. Thank you so much. We have one last follow-up question and then we'll get into like the Q&A questions from like the audience. So like this is like the big question, like what is HoloLens? Like how would you explain like what it is? Like where is it used? Like it's obviously one of the first products in its space. What's its use case in like the industry or for like consumers, and like just what is it in general?
Yeah, so HoloLens is the primary AR device or mixed reality device in the market right now. And it has world-facing cameras, human-facing cameras, microphones. As I said, in all the three areas, it's trying to understand the human, it has a computer, and trying to understand the environment and making connections throughout. The big difference is that they are glasses like your normal glasses, and through them you're seeing the real world. It's not occluding your real world like a VR, but in the real world, it is placing holograms for your interaction. It is different than seeing the real world through a phone's camera, because then again you are seeing the real world through a video stream. But this is literally glasses, like through which you are looking at the world, and that brings up. Imagine a few years now. Of course, right now it is focused on enterprise primarily, and that's where you're getting the most traction. But imagine the future when things become lighter and ubiquitous as a consumer device. Now, it could open up a lot of avenues. But even before going there, let's talk about what it does now. There are three big areas I feel where it is being used. And there are a lot of areas, but if I were to choose my one I like the most, I would say the medicine, medical hospitals. Surgery, which was not possible before. People can now surgeons can look at patients, overlay the information right on their bodies, as I talked about incision points and whatnot, without moving their head back and forth between a monitor in the back of the surgery room or something, right? And as they're moving their hands are being tracked, their eyes are being tracked, and every information is being overlaid exactly at the time, at the place they need in 3D. Right, so that's a big area. The second is education. I mean, I remember I used to hate some part of chemistry in my school days, where you have all these chemical compounds and they've been drawn on a flat piece of paper. It's so hard to understand how they appeared in 3D. Now you could actually see them in 3D and manipulate them. Think about, that's a huge area. I'm just giving you a chemistry example. Anatomy. It's already being used in medicine school, where students are using it to do some work on cadavers and so on. And then factory floors. People, when they go and they're working on very heavy machinery and complex machinery, many times it's very hard to do remote assist. How do exactly a worker knows what exactly needs to be fixed? If they're wearing a device, they are seeing, and the remote assist is seeing what they are seeing and what they are doing. And they now can work in real-time collaboration to fix things up. So I feel these are big, big areas. There are many others in terms of designing spaces and everything else. But yeah, that's.
Thank you so much for the answer to that question, Mudit. I'm also like super excited about like the things that AR is able to do in the future. Especially, I think I was particularly interested in how it can be used in the surgery room. That's really interesting to me. But now we're going to be moving on to the Q&A questions. We have quite a few of them, and I'm not sure if we're going to be able to get through all of them. But we're going to get started with the highest, the one with the most likes, which is by Yash, which is when developing or exploring new tech ideas to pursue, how does your role as a researcher with heavy technical experience differ from a less technical role like product management?
I see. That's a great question. I would say they both have to go hand in hand. And I could actually use an example, which I did in the recent past. If you are trying to explore a new area, there are many aspects of it, especially in industry, and that's another part of how industry research differs from academic research. You would have a hardware expertise and software and security, and there's so many around it, which you have to kind of ace to make a product well worth its cost. So as a researcher, you would be really focused on how the problem can be solved. Whereas as a program manager, the first question comes first, which is the functional requirement, why the problem needs to be solved in first place, and what problem needs to be solved and why should be solved. So that's more of a program manager's role. And from our perspective, it's more about how it needs to be solved. But they need to work together, because many times the problem which needs to be solved, when you're looking at the cutting edge problems, cannot be solved. You look up and say, no, this is not technically possible today. So you change it and say, maybe I can solve this. Does this produce what you want? You go back to the PM and you say, maybe this. And that's how you do that handshake and make things work.
Awesome. And we have another question from Anonymous, which is, what, in your opinion, is holding VR back from widespread consumer adoption? And what advancements are needed to make VR a daily part of everyone's life?
Is it specifically about VR or in general AR, VR?
I mean, they mentioned VR, but I think I would also would want to hear about AR.
Yeah, I think first, the commonality between both of them is when we talk about consumer devices, and especially which you have to wear on your head, which is the primary area. I don't wear glasses, but whenever I do, my sunglasses and it's not sunny, I just don't want to wear it. I just remove them, right? It has to be light, and you don't have to charge it 20 times a day or something. So it has to follow all those paradigms of what our research has happened in the past of people wearing glasses. They've kind of aced it, and right nose pads, the right sizes, the right weight. At the same time, the reason why you have a phone in your pocket today versus 20 years ago is the value it provides to carry that extra weight. And it's in your pocket. Thighs can carry much more than the head. So now that something coming on your head has to be very valuable for you to carry it all the time. So I think we are still in that process of finding the right value throughout the experience. We still have aced, as I said, areas of time, like in a surgery room and you are in a factory floor and blah and blah. But what would it need to do it throughout? Like you have it on your head and you don't want to take it off. As I said, weights and power and other things would happen, but even the experiences need to happen from that perspective. That is, I think, a general answer for both AR, VR. But from a VR perspective, and my personal take is that VR, since it occludes you from the real world, has to have that easy access mode to access the real world when you want to, and not. At the same time, untethered, which are already there market things in the market for certain scenarios. Again, if you talk about ubiquitous scenario users, then it will be untethered. But at the end, I think they have to merge. It cannot be a separate AR, VR kind of a thing. As I said, that's why we use the better word mixed reality. When you want an experience, you don't want to see the real world, you should probably fade in and just show you the digital world. Otherwise, fade out and show you everything around.
A perfect segue into our next question, actually. You're talking about the user experience and who defines it. So Remus is asking that with product managers and designers, how much responsibility should engineers have in defining the end user experience?
It's a great question. It's a very contentious one also, right? I mean, I could actually turn this in and ask how much, I don't know, how much should a biologist have an opinion in how computers should be made? And you could just say, why should they have an opinion? So you could very well say, why should an engineer have an opinion about how things should be designed? If at the end, you pick up a phone in the market because it's beautiful, it's nice and elegant, whatnot. You don't care if it has the best algorithm at the end of the day, unless it gives you the better results, which really should matter and so on, right? So I think that is very. So from that perspective, I would say, yeah, it's probably less of the matter. However, if you disconnect the designers and the PM from the engineers, that's where we fall back to the problem, which I was speaking 5 minutes earlier, where you are hallucinating a product which doesn't have a real solution in the middle. So engineers should have a say in a sense where when the requirements come in, what the vision of the designers and the program management is, how much of that is possible, achievable, given the current problem at hand and resources and everything. And then that's how the reinforcement should happen on both sides. So that way they are influencing them heavily because they are the one actually building it. But they are not directing the other way around. So that would be different if you have a product design team and you have an engineer who's been only talking about the design aspect of it. I think that's bad. You should talk about what is feasible and what is not in the room.
I think we have time for 2 more really fast questions. Here's a question from Pranchu. What books or platforms do you suggest to get started learning about AI and its possibilities? I know you touched on this before, but yeah, just reiterating.
Yeah, for sure. I think this is very important. I feel Coursera is a great platform personally. It has great courses. Again, doing linear algebra to begin with, some machine learning fundamentals. Before you even touch a DNN, maybe swear you won't touch DNNs before you spend I don't know how many months on fundamentals and basics or 101 courses. But then after that, a few courses by Andrew and Jeffrey Hilton are amazing. There are other courses which you'll go and you can see the ratings there. But at the end, it's also very important, apart from understanding the theory, which Andrew does amazingly well, and Jeffrey, to start playing with some real data. And that's where I was talking about Raspberry Pi, buying a couple of those and solving some problem which you really care about. It could just be a running car in your house or watering a robot just water plants every 1 day or something, recognizing some individuals in the house, whatever that case. But taking that and implementing it is the real deal. I've done this in the past where only focus on theory, and then when you start implementing and you really struggle, especially because things are evolving very fast. So what you read in theory and what tools are available to implement it, you got to know them. And once you are in that water, you now then understand how things are changing there as well. That would be, I think, and then of course, in case if you're looking at a grad school from a grad school perspective, there are always opportunities as internships or go and meet great people. I think you'll be surprised how many people who you feel are unapproachable are approachable. and you can see if they give you some new ideas which they feel are possible, but they don't have time to do, or they haven't position for you to actually go and experiment with them.
Yes, thank you so much again for all your insightful answers. I think that's all the time. We don't want to run overtime, so I think I know there's some more questions in the chat, but we can get to them. But again, like on behalf of the organization, Tiago and I, and like everyone watching, thank you so much for being here. I know it's like tough on a Saturday afternoon to come and like talk to college students about your experiences, but we really, really, really do appreciate it. And like all of your advice is so invaluable, especially for students that are just like on the brink of maybe like going into research or maybe going into like some more technical fields, especially in the engineering space. So thank you again for being here. And yeah.
Thank you. Yeah, thank you, Tiago. And it's been amazing to talk to you, to discuss all these things. Again, thanks for all the people who joined in. Many thanks and have a great day.
Awesome.
Thank you so much.